The Internet operates without a central traffic controller. There is no overarching system dictating exactly which devices get to send data or when. Because of this, network congestion is a constant physical reality. To see how this manifests, consider a packet of data that successfully navigates multiple router hops before hitting a bottleneck. In networking theory, this is known as Scenario 3. Data travels cleanly through the first 3 nodes. But at the 4th junction, the volume of arriving data exceeds the link's outgoing capacity. The packets pile up, and eventually the system simply destroys them. When a packet is dropped this far downstream, the upstream transmission capacity used to get it to that 4th node is permanently wasted. This happens because intermediate routers have finite memory buffers. They cannot hold excess packets indefinitely. When those physical buffers fill up, any new arriving data is dropped. This creates a distributed engineering problem. Isolated endpoints, your laptop and a remote server, must discover the exact capacity of the network path between them. If they guess too high, they overwhelm the intermediate routers. Endpoints solve this probing problem using the Transmission Control Protocol, or TCP. TCP relies on a state variable called the congestion window, or CWND. This is a numerical limit on exactly how much unacknowledged data a sender is allowed to transmit at any given time. We can map the behavior of this algorithm on a Cartesian plane. This chart tracks the congestion window on the y-axis against the number of transmissions, measured in round-trip times, on the x-axis. On the right, we track the exact values for 2 state variables, CWND and the slow start threshold, or SS-thresh. The congestion window is governed by a rigid state machine that dictates exactly how fast to increase output and how to retreat when the network pushes back. The rules governing the congestion window provide the logic that allows billions of independent devices to share the same physical links without driving the system toward a total collapse. To see these rules in action, we can run a forensic trace of a standard TCP session over 10 transmissions. For transmission 1, our starting state variables are a congestion window of 2 and a threshold of 8. The system enters its initial phase, slow start. While it is called slow start, the growth rate during this phase is actually exponential. The rule here dictates that the congestion window doubles every round trip time. For every successful acknowledgement received, the window increases by 1 maximum segment size. By transmission 2, the window reaches 4. If those packets are also acknowledged, the window doubles again. At transmission 3, the congestion window updates to 8. Here, a state transition occurs. The window has reached the slow start threshold limit of 8. This transition is necessary because exponential growth is too aggressive to maintain once the sender reaches its known safe capacity limit. For transmission 4, the algorithm shifts into the second state phase, congestion avoidance. In congestion avoidance, the growth rule shifts to linear. The congestion window now increases by only 1 segment per round trip time, probing the remaining network bandwidth cautiously. At transmission 5, a critical fault occurs, a timeout. The expected acknowledgements for the sent data never arrived. A timeout suggests that an intermediate router's buffer overflowed and the packet was dropped. The algorithm responds by updating the threshold. The new threshold is set to half of the current congestion window. Half of 9 is 4.5, rounded to 4. Then the transmission rate is reset. The congestion window drops all the way down to 1. By reducing output to a single segment, the algorithm immediately relieves pressure on the network. This demonstrates how TCP prioritizes the stability of the shared network over individual speed. Following the drop, the algorithm re-enters slow start for transmission 6, doubling the window to 2. By transmission 7, the window doubles again to 4, hitting the new lower threshold limit and shifting the phase back to congestion avoidance. From here, the algorithm returns to its linear climb. Through transmissions 8, 9, and 10, the window increases incrementally to 7. Not all packet losses handled this severely. A drop can also be detected by receiving 3 duplicate acknowledgements. 3 duplicate ACKs indicate mild congestion. It means packets are still flowing through the router. They are simply arriving out of order because one was lost. Modern implementations like TCP Reno use a fast recovery bypass for this scenario. Instead of resetting the window to 1, it only drops the window to the new threshold plus 3 segments. These diverging state transitions allow TCP to apply proportional penalties based on the specific physical severity of the network fault. Viewed over hundreds of transmissions, a distinct weave pattern emerges: additive increase, multiplicative decrease, or AIMD. The linear upward slopes map to additive increase, growing by one segment per round trip. The sharp drops are multiplicative decrease, slashing limits in half after a loss. The individual rules of TCP result in this self-regulating sawtooth pattern, a continuous, automated negotiation between speed and stability. Standard TCP Reno works well on traditional networks, but its linear increase is too slow to reclaim bandwidth on modern high-speed pipes. To address this, engineers developed TCP Cubic, an evolution designed to replace simple linear growth. Cubic calculates the window size as a cubic function of the time elapsed since the last packet loss, rather than relying on incoming acknowledgments. This comparison shows the difference in recovery. While Reno uses a straight diagonal climb, TCP Cubic aggressively shoots upward before leveling off just below the previous peak. This allows the protocol to rapidly reclaim safe bandwidth, while probing more cautiously near the exact point where the previous failure occurred. As network capacities scale, the distributed algorithms governing them must shift from linear growth to more complex cubic curves to keep pace with modern hardware.